Download this code from codegive.com, link in the description below. ADA003 Lesson 3, Access Types, Pointers, a comprehensive tutorial. This lesson delves into the powerful concept of access types, often referred to as pointers in other languages like C or C++. Access types in Ada allow you to manipulate data indirectly through references, providing flexibility and control over memory management. We'll cover the fundamentals, explore different kinds of access types, and demonstrate their use with practical examples. 1. Introduction to access types. At their core, access types store the memory address of a value of a particular type. Instead of holding the value directly, an access type holds the location of the value in memory. This indirect access brings several advantages. Dynamic memory allocation. Access types enable you to allocate memory at runtime, creating data structures whose size isn't known at compile time. This is crucial for dynamic arrays, linked lists, trees, and other data structures. Sharing data. Multiple access variables can point to the same data, allowing different parts of your program to share and modify the same information without copying it. Creating recursive data structures. Access types are essential for building recursive data structures like linked lists, where each element contains a pointer to the next. Passing large data structures efficiently. Instead of passing entire data structures to subprograms, which can be costly in terms of memory and time, you can pass access values, which are small and represent the location of the data. 2. Declaring access types. Ada offers two primary types of access types. Access to object types. These point to objects that hold data values. Access to subprogram types. These point to subprograms, procedures or functions, allowing you to pass subprograms as parameters or store them in data structures. Let's focus on access to object types first. The general syntax for declaring an access to object type is where access underscore type underscore name is the name you choose for your access type. Type underscore name is the type of object that the access type will point to. This can be any Ada type, including integers, floats, records, arrays, or even other access types. Example. 3. Creating and using access values. After declaring an access type, you need to create access values, also called pointers, and associate them with actual data. There are two main ways to do this. Allocating storage using new *. The new keyword is used to dynamically allocate memory on the heap and create a new object of the specified type. The new operator returns an access value that points to the newly allocated object. Explanation. One type integer underscore pointer is access integer, declares the integer underscore pointer access type. 2 int underscore ptr, integer underscore pointer, declares a variable int underscore ptr of type integer underscore pointer. At this point, int underscore ptr doesn't point to anything, it's uninitialized and potentially contains a garbage value. 3 int underscore ptr equals new integer, allocates memory on the heap to hold an integer and assigns the address of that memory to int underscore ptr. Now, int underscore ptr points to a valid memory location. 4 int underscore ptr dot all equals 42, this is the crucial part for accessing the value at the memory location int underscore ptr points to. All is used to dereference the access value, meaning we are working with the actual integer object stored at that address. We assign the value 42 to this integer. 5 put underscore line, prints the value that int underscore ptr points to. We use all again to access the value. 6 free, int underscore ptr, deallocates the memory that was allocated by new. This is important to prevent memory leaks. Ada's garbage collector may eventually reclaim the memory if you forget to do this, but relying on the garbage collector alone isn't considered good practice, especially for long-running applications or systems with limited memory. Note: Ada versions after 2005 do not generally require an explicit free. But it's good practice to know about it and to use it when appropriate. Accessing existing objects. You can also create an access value that points to an existing named object. This requires the use of the access attribute. Explanation: 1 my_integer, integer equals 10, declares an integer variable my_integer and initializes it to 10. This variable is allocated on the stack, or in static memory if declared at the package level. 2 ptr equals my_integer access, this is where the magic happens. My_integer access creates an access value that points to the memory location of my_integer. ptr now contains the address of my_integer. 3 changing my_integer will change the value that ptr.all accesses, because ptr points to the same memory location. Important notes: null access values. An access value can be null, meaning it doesn't point to any valid memory location. Accessing ptr.all when ptr is null will raise a storage_error exception, or sometimes a constraint_error. Always check for null before dereferencing an access value. Accessing values using .all as mentioned earlier, .all is the operator used to dereference an access value. It gives you access to the actual object stored at the memory location pointed to by the access value. Memory management. While Ada has a garbage collector, it's generally good practice to explicitly deallocate memory when you're finished with it using the free subprogram. However, the exact behavior of the garbage collector can vary depending on the Ada compiler and its configuration. Explicitly freeing is crucial for real-time systems or applications where memory usage must be tightly controlled. Starting in Ada 2005, garbage collection became mandatory, making explicit free calls less critical in many situations. 4. Access types to records. Access types are frequently used with records to create dynamic data structures. Let's create a simple linked list example. Explanation: 1 forward declaration type node. This is a forward declaration. It tells the compiler that the node type will be defined later. This is necessary because the node record contains a field, next, that is of type node_pointer, which itself is an access type to node. Without the forward declaration, the compiler wouldn't know what node is when defining node_pointer. To node_pointer definition: type node_pointer is access node. This defines node_pointer as an access type that points to node objects. 3 node record definition: type node is record, and record. This defines the node record. Each node contains an integer value, data, and a pointer to the next node in the list, next. 4 free procedure: procedure free is new Ada.unchecked_deallocation. This is crucial. Ada requires a special free subprogram for each access type that uses dynamic allocation. Ada.unchecked_deallocation is a generic package that provides this functionality. You must instantiate it for your specific access type. Note the use of object and name to tell the system what is being deallocated. Without this procedure, trying to call free, node ptr, would result in a compiler error. 5 head pointer head, node_pointer equals null, this is the head of the linked list. It's a pointer to the first node in the list. it's initialized to null to indicate that the list is initially empty. 6. Insert underscore node procedure asterisk. This procedure adds a new node to the beginning of the linked list. It allocates a new node using new, sets its data field, points its next field to the current head, and then updates the head pointer to point to the new node. 7. Print underscore list procedure asterisk. This procedure traverses the linked list from the head to the end, where next is null, printing the data value of each node. 8. Free underscore list procedure asterisk. This is very important to prevent memory leaks. This procedure traverses the entire linked list, freeing each node's memory using the free procedure. Asterisk important asterisk. You need to be careful when freeing nodes in a linked list. You need to keep track of the next node before freeing the current node, otherwise, you'll lose the rest of the list. 5. Access types to arrays. You can also create access types that point to arrays. This is useful for dynamically allocating arrays and passing them to subprograms. Explanation asterisk. 1. Integer underscore array type asterisk. Type integer underscore array is array, index underscore type, of integer, defines the array type. 2. Integer underscore array underscore pointer type asterisk. Type integer underscore array underscore pointer is access integer underscore array, defines the access type that points to integer underscore array objects. 3. Allocation asterisk. My underscore array equals new integer underscore array, allocates memory on the heap for a new integer underscore array. 4. Accessing array elements asterisk. You access array elements using the standard array indexing notation, just like with statically allocated arrays, my underscore array, I. No.all is needed for accessing array elements directly. 5. Deal location asterisk. Free, my underscore array, deallocates the memory used by the array. Again, you must instantiate ada.unchecked underscore deallocation for the integer underscore array underscore pointer type to use the free procedure. 6. Access to constant and access to variable types. Ada provides finer control over access types with qualifiers for constants. Asterisk access constant allows read-only access to the data it points to. You cannot modify the value of the object through the access value. Asterisk access variable is the default if you don't specify constant explicitly. Allows both read and write access to the data it points to, provided that the underlying object is not declared constant itself. 7. Access to subprogram types, brief overview. While this lesson mainly focuses on access to object types, it's worth briefly mentioning access to subprogram types. These allow you to treat subprograms as data. You can declare variables that point to subprograms and call the subprograms through those access values. 8. Important considerations and best practices asterisk asterisk. Asterisk dangling pointers asterisk. A dangling pointer is an access value that points to a memory location that has already been deallocated, freed. Dereferencing a dangling pointer leads to undefined behavior, often causing crashes or unpredictable results. Always ensure that access values point to valid memory locations. Setting pointers to null immediately after deallocation is good practice to prevent accidental dereferencing of dangling pointers. Asterisk memory leaks asterisk. A memory leak occurs when you allocate memory using new but fail to deallocate it using free when the memory is no longer needed. Over time, memory leaks can consume all available memory, leading to program crashes or system instability. Carefully manage dynamically allocated memory by always freeing it when you're finished. Asterisk garbage collection asterisk. As mentioned earlier, Ada's garbage collector may reclaim memory that you've forgotten to free. However, relying solely on the garbage collector is not always reliable and is generally not considered good practice. Explicitly deallocating memory is more deterministic and gives you better control over memory usage, especially in resource-constrained environments. Asterisk checking for null asterisk before dereferencing an access value using .all, always check if it's null to prevent exceptions. Asterisk ada.unchecked underscore deallocation asterisk remember to instantiate ada.unchecked underscore deallocation for each access type that you use with new, allowing you to use the free procedure. Without this, your code will not compile if you try to call the free procedure with a specific access value. Asterisk access to subtypes asterisk when using access types, ensure that the access type and the object it points to have compatible subtypes. You can use subtype constraints to enforce tighter checks on the data being accessed. Asterisk access to protected objects, use access types to access data in a thread-safe manner. 9. Summary. Access types, pointers, are a powerful and essential feature of Ada that allows you to manipulate data indirectly and manage memory dynamically. This lesson covered the basics of access types, including their declaration, creation, and use, as well as the important concepts of memory management, dangling pointers, and garbage collection. By mastering access types, you can create more complex and flexible data structures and algorithms in Ada. Remember to always be mindful of memory management and potential errors when working with access types to write robust and reliable software. Practice with the examples provided and explore other advanced uses of access types to deepen your understanding. Good luck.